Hey, it's Tony from Adafruit, and in this video I'm going to start a series on CircuitPython and how to use all of the basic functionality in CircuitPython. So things like controlling digital inputs and outputs, analog inputs and outputs, all kinds of things, interfacing with I2C, SPI devices. We'll get to a lot of that stuff, but in this video I'm going to start just with the basics of digital inputs and digital outputs, basically on-off signals. And I've done some videos on this before, so I've done videos with the Raspberry Pi and with MicroPython, but in this video, like I said, this is going to focus on CircuitPython and some of the specifics of the CircuitPython APIs. So we'll see how to read digital inputs and how to talk to digital outputs like control LEDs and things like that. So we'll dive in and we'll get started with this. You might notice the set's a little bit different. I'm doing some spring cleaning right now, so you'll probably see some more stuff in the future in the back, but I figured I'd just start with a clean slate to get started with. And like I said, this is all going to be focusing on CircuitPython, so to follow along, you're going to want a board like the Circuit Playground Express or maybe the Gemma M0, so some kind of a board that can run CircuitPython. I've done lots of videos on some of the CircuitPython boards and functionality we have. Look in the video description below when this goes up on YouTube, and I'll put links to all of the hardware that I talk about and all of the web pages and things that I might link to so that you can find more details on what we're looking at. And for this video, I'm actually going to use the Gemma M0. So this is the little version of Gemma, which is our tiny little wearable board, but it uses the SAMD21 microprocessor and actually ships with CircuitPython out of the box. So when you get this, it will be running CircuitPython, and you can get started immediately. You don't really need to do anything. But if you have a board like the Circuit Playground Express or maybe the Feather M0 or the Metro M0 board, you'll need to first load CircuitPython onto your board before you get started. And conveniently enough, I've actually done a whole bunch of videos on how to do that. So I have a video for Chrome OS, for Windows 10, which would also work on Windows 7 and earlier versions, and then also for Mac OS. So there are 3 different videos, and I show a basic workflow of how to load CircuitPython onto a board, and then how to set up your editor so you can edit code, how to access the serial terminal on the board so that you can do things like interactively write Python code and see the results of it. So check that out. I'll put a link in the description below to all 3 of those videos. So start there if you're completely new to MicroPython or CircuitPython. That'll get you started and show you how to load CircuitPython onto your board if you need to. If you're using the Gemma M0, it's actually got everything you need out of the box, although it doesn't hurt to watch those videos to see how you can update the version of the firmware and load the latest things. So we'll get started here. I'll jump to the main view that I have, and we'll see what I've got in store for us. Let's see. We'll go to the desktop there, and we'll open up the browser here also. Oops, and let me actually, yeah, there we go. Okay, just making sure that the CPU usage doesn't get too high. In the upper right hand corner, I have a Gemma M0 right here, and this is actually connected to my computer right now. And so it's actually just running the default main sketch that comes with the Gemma M0. I think it's stopped right now, but it will just take the little LED and it'll cycle the colors on it. And with the Gemma M0, it has a NeoPixel built into it, so that's the green light right here. There's also another little just red LED. It's a user controllable LED, so you can use this as a status indicator. There's also a power switch on the Gemma M0, so if you plug this in and nothing happens, make sure the switch is in the on position. There's a tiny little switch right here, which is kind of handy if you're making a little project for this. Okay, so we'll get started here. And like I said, this video is going to be about digital I/O, so digital inputs and digital outputs. And basically, this is going to show you how to control a digital output, so how to turn an LED on and off, for example. But I'll talk about there's some more things you can do with the digital output than just controlling an LED. And then we'll also see how to read a digital input, so something that gives you an on or off signal, for example, like a switch or a button. We'll see how to read that. But I'll also mention there are some more interesting examples of things that give you a digital output that aren't necessarily like a switch or a button in this case. So let's get started here. I'm going to switch to the serial REPL. So for most of this video, I'm just going to use the serial REPL, and I've talked about this in previous videos. But basically, one of the big features of CircuitPython and MicroPython is that you have what's called a REPL, the read, evaluate, print loop. And that's basically a prompt where you can type in Python code that will be executed as soon as you press enter. And so that's kind of cool because you can explore and you can learn by just connecting to the REPL and running Python code. You don't have to install an editing tool, you don't have to upload code, you don't have to see the results of it. You can just connect to the board and get started and play around with it. And so that's exactly what we're going to do. And a great way to get started to maybe follow along and just play with your hardware is to use the serial REPL. And then you can create a program later and save it onto the board, and then it will run that program that you've created ahead of time. But this is great to explore with. So I'm going to connect to the serial REPL, and like I said, go back to those 3 videos I mentioned for Chrome OS, Mac, and Windows, where I show on each of those platforms how to connect to the serial REPL. On Windows, you might need to use a tool like Putty. I'm on Mac right now, so I'm going to use the screen command that's built in. And then on Chrome OS, you need to install something like BeagleTerm as a program that can do it. But I'm going to connect to the serial terminal on this device. So it's dev tty USB modem 29 at 115200 baud. And the first time I connect, nothing really seems to happen. And especially with the Gemma M0 out of the box, you're going to connect and you won't see anything in the REPL. And even if you press enter, you're not going to see anything happening. And that's because there's a main program that's running on the board right now. So I need to stop that program so I can get back to the terminal. So press Control C, C as in cat. So I press Control C, and that just interrupts the main program. It says, hey, stop what you're doing and let me type in Python code. And so now I get my Python prompt here. I can say, hey, hello world. So it's good to make sure you can get to this point. And then at this point, I'm just going to play around with an LED that's built into the Gemma board itself. So like I mentioned, there's a little LED, it's a red one that's on the board, and it's connected to one of the digital inputs and outputs of the Gemma processor, the SAMD21 on there. So we can actually control that by setting it to a high or low logic level to turn the LED on or off. So we can do kind of the hello world, blinking an LED, all in Python code. And with CircuitPython, so the way that you talk to digital inputs and outputs is using this module called Digital I/O. And I'll put a link in the description so you can go to this page. This is the CircuitPython API documentation. And so this is the module that we need to use. We're going to use this module, and it basically has like one class inside of it that we care about. There's a digital in/out class, which creates an object that can be either a digital input or a digital output. And I'll show you, you can switch between those 2 different types. And that's it. So once you have a digital input or output, then you've got control over either reading or writing a digital signal. And like I said, a digital signal is an on or off signal. So imagine like a light switch. So you flip the light switch on, the lights come on in your room, that's an on signal. You flip the switch off, your lights go off, it's off. There's no in between, so you can't kind of flip the switch halfway in between on and off and get kind of half brightness. You can with some lights, but that's not a digital kind of input or output. You know, you've got some kind of a dimmer that's controlling that. So it's really just on off. You know, flip the switch on, it goes to a high logic level. And in electronics, when we say high logic level, we mean some kind of voltage. So for this processor and for this board, a high logic level is 3.3 volts. For some boards, that high logic level is 5 volts, like an Arduino board, for example. Most of them are 5 volts. It really depends on the processor, whether it's a 5 volt or 3.3 volt digital high logic level signal. And so you might have to look at maybe your board's kind of description or sometimes the data sheets for your processor to figure that out. But generally, it's 3.3 volts or 5 volts as a high logic level. And then a low logic level is anything that's at a ground or 0 volt level. So something that's basically not at a high voltage level, you're at a low level, and so that's off effectively, or a low logic level. So let's play around with controlling the LED on this board. And I'll show you there are 2 modules that we need to import to deal with this. The first is the board module. And so the board module basically has definitions for all of the pins that are on your board in CircuitPython. So you notice I type import board, that's the standard Python syntax for importing a built-in module. But I can also run this dir board command, and this is kind of a way to tell Python to list everything inside of a module. So this is listing all of the high-level functions or variables or global objects that are inside of here. And you can see this lists a bunch of objects that are defined in this module. And these all happen to be objects that map to the different pins or the inputs and outputs on the board. So you notice there are like 6 of these little circles on the Gemma M0. So most of these are digital inputs or outputs. Some of them are like a ground or a 3.3 volt output. But you can see that, for example, up here is a D0 little circle or pin. And so notice that there's a D0 object inside of here that I can use to reference that. Now, if I look at the LED, and it's hard to see on this camera view, but there's a little L next to it. And so notice there's an L object inside of here. And conveniently enough, that's basically the pin that's connected to the built-in LED of this Gemma M0 board. So if I create a digital in-out object that's using this board.L pin, then I can either set that high or low to turn on or off the LED. So let's do that. So let's import the digital I/O module. Might help if I spell it correctly. There we go, digital I/O. So again, Python import command that imports the module. You do this once at the start of your program or once in your REPL session. And then inside of here, like I said, you can use that dir command again to just see what's inside of here, or it's probably a little bit easier to go to the documentation. And so this documentation lists, like, these are all the high level things that are inside of this module. But conveniently enough, you notice that these match the same things that we see right here. There's this name thing. This is something that Python does internally. It creates some of these magic variables that are kind of internal to Python in some ways. But the digital in-out class is what I care about. So I need to create an instance of this that's connected to that L pin on the board. So let's do that. We'll say LED equals digital I/O. So I need to reference the digital I/O module because I've only imported the module name. I haven't imported anything from the module. So since I haven't done that, I can just reference the module name and then anything inside of it. And then I want to create a digital in-out object. And then this takes one parameter. So it needs to know the pin that you want to connect this digital input or output to. And in this case, I'm going to use the board.L pin. And so that's from the board module, that L object that we saw right here. And so that's going to be connected to the LED that's on the board. So I do that. And by default, this LED is actually created as an input. So it's not an output. It's not set to anything. And that's just a safe default because when a pin is an input on most boards, it's put into a state where it's not really connected. Like, it's not going to be on, it's not going to be off. You know, if there was something connected to this, like, you know, imagine a relay or a switch or something like that, it's not immediately going to like flip that to an off state or an on state. You know, it's not going to give it some default value because in some cases that might not be good. Like, you know, like I said, you might have a relay connected to this that's maybe controlling, you know, whether, you know, I don't know, maybe you have a bucket of water that's about to dump on someone or something like that. So you don't want to create your digital object and then have it just immediately set that false and then, you know, move your relay and then suddenly, or move your solenoid and dump something on someone, and that could cause some problems. So everything defaults to an input. But to switch to an output, it's actually pretty easy, and it's basically a function that you call. So switch _to _output on that LED object that I created. So this is going to switch it from a digital input to a digital output, which means that I can control whether this is at a low or high logic level. And I believe it defaults to setting it down to a low logic level. So this is actually going to just turn the LED off effectively if it was on already. But I'm going to say switch to output. Okay, now at this point, this LED object is a digital output that I can control. And so there's a property on this object that I can set to change it to a high or a low logic level. And that's basically the LED.value property. And I can set this to a Boolean value, like a true-false value. So I can say this equals true, and I do that, and notice the red LED just came on the board. And so that just set that LED output to a high logic level. So it set it to 3.3 volts. And the way that this board is built, when there's 3.3 volts on that L pin, then that's going to light up the LED. So there's a resistor in line with it, and then the LED, and then it's connected down to ground. And if I set the LED.value to false, then hey, surprise, surprise, the LED turns off. So you see it goes off. So I've just lowered it down to a low logic level. So I can go, you know, true to turn it on and false to turn it off. And then if you want to blink it, it's as easy as just putting that into a loop. So let's say like 10 times. So let's import the time module so that I can delay in between my blink. And then just for I in range 10. So this will loop 10 times. And then let's say LED.value equals true. So we turn it on. Time.sleep for half a second. LED.value equals false. So we turn it off. Time.sleep for half a second. And so after I do this, and then I need to de-indent or tell Python that I'm done with everything inside this for loop. And I'll press enter. And now notice it's running, so it's actually blinking. So it's on for half a second, off for half a second, on for half a second. And it's going to do that 10 times total. And so that's hello world. We've basically just controlled the hardware just by controlling that digital output, by setting that to a high or a low logic level. We're able to control that LED. Now you could wire up your own LED if you wanted, and I'll actually show you, so it's kind of interesting. Let's use a multimeter and let's look at the voltage of a digital output when I set it high or low, just to really kind of drive home the point that a digital input or output is really just a voltage level. It's either a high or a low voltage level. So let's do this. Let's connect my multimeter. Let's connect the voltage reading pin to the D0 output at the top here. And then the ground, I'm going to connect to the ground on the Gemma M0 board. So this is connected to my multimeter right here. Let's zoom out a little bit so we can see all this. I'm going to put this into the DC voltage reading range. Okay, so I'm reading basically the output of the D0 pin right now. And you can see it's around like 3.6 volts. There's nothing that's really using that pin yet. So the value that it's going to get is kind of random or indeterminate. Maybe something ran earlier that set it to a low logic level and it just happens to be down at that level. But until I actually control this as a digital output, it could be any value. It could be high, it could be low, who knows what it is. It's basically, it's a floating state sometimes also, where it's just oscillating with all this electronic noise between high and low logic levels. Okay, so let's create that D0 pin as a digital output, just like I did the LED pin before. So if you go back to that board module, if I list everything in here, notice that there's that D0 object inside of there. So I want to create a digital in-out object using that. So let's say D0 equals my digital IO module dot digital in out, and I'm going to point it at the board dot D0 object in this case. And again, this starts out as an input, so it's not really setting itself to any high or low logic level. But let's say switch underscore to output, like I did before. And okay, notice something just changed. So my multimeter here now is reading basically 0 volts, like 1 millivolt. This might as well be 0, and it's auto ranging. So let me just manually set the range to volts. So there's the volt value. You can see here's the high order one. I guess here let's just change the range a little bit. There we go. So now we have 2 digits of voltage of the high order, and then there's the tenths and hundredths placed below there. So 0 volts. There's nothing controlling this. This is not turned on. This is off. And so I can actually tell that if I do D0.value equals false, that's effectively what's happening here. But let's see what happens when I set this to true. I do that, and boom, check that out, 3.3 volts effectively, exactly actually. So that's perfect, that's what I expect to see. So I set this to a high logic level, and I get the high logic voltage for this board, which is 3.3 volts. And I can set this to false, and I go back down to 0 volts, or a ground level basically. So just kind of driving home that point that, this output right now, I'm controlling the voltage of it. And I don't have complete control. I don't have, I can't set this to like 1.8 volts. But maybe tune in for next week's video and you'll see some ways that you can do that. But I can control this as 3.3 volts or 0 volts. So I can go in between those two extremes. I can be on or off. And so that's pretty handy. So, just to show again, I can turn that off and I can turn that on. So with everything still connected here though, let's get a little more advanced. Let's actually take an LED and let's wire up a standalone LED. Just to really show that I can actually control this voltage and I can do things with this. So what you're going to want for this point is you're going to need an LED. So I have, this is just a nice little blue LED. You're going to need a resistor of some sort. And you're going to want a resistor that's somewhere around like 300 to 600 ohms or so. The exact value doesn't really matter. It limits the current that's going to run through this LED. If you don't have the resistor, then you might damage your board or your LED because it's going to try to send as much current as possible through the LED. And LEDs don't like that. They can explode, not explode, but you can burn them out, or your board might not like that and you might damage your digital output. That's why you always want to use a resistor in line with your LED. And then the LED, it has 2 legs on here, and so it's a little hard to tell, but you can see one of these legs is longer than the other. So this is the longer leg, and that's the shorter leg. Basically, the shorter leg is the cathode, and so that's where you want to connect the ground, and then the longer leg is the anode. and that's where you want to connect the power, your input to your LED. So if I apply 3.3 volts to the longer leg, and then I have my shorter leg connected to ground through a resistor that's going to limit the current, then this LED is going to turn on. And so that's exactly what I want to do. So I'm going to use a little breadboard here, and I will plug in LED. And then what I'm going to do is I'm going to connect, so the longer leg of the LED, I'm going to connect to, and actually let me zoom out a little bit so we can see all of this. So the longer leg, I'm going to connect to that D0 output. So I'm going to use some alligator clips here to make that happen. So let's connect D0. So I'm also going to keep the multimeter hooked up just so you can kind of see both the voltage and the output here. Handy thing about this Gemma board is that you can connect alligator clips really easily. You can do the same thing with Circuit Playground also. So it's got those handy little connections that you can put an alligator clip on. Okay, so I've connected that to the longer leg is going to my digital output. And then the shorter leg, I'm going to take my resistor and I'm going to connect it to the shorter leg. And then I'm going to connect the other end of the resistor to the ground on my board. So we're going to take this white and connect this to the ground that my multimeter is also connected to. So, yep, looks like I'm making a connection there. Okay, so, and remember, I've controlled this D0 output, and it's at a low logic level. You can see 0 volts, so the LED is not turned on. But let's see what happens when I set this to true. Check that out, the LED just turned on, and you can see 3.1 volts or so on the output there. And if I set that to false, LED turns off, goes down to 0 volts. I set it to true, and it turns on. So that's pretty cool. And again, just kind of showing that a digital output is really nothing more than an output where you can control the voltage between a high voltage, where it's usually 3.3 volts or maybe 5 volts on some boards, or a low voltage of ground or 0 volts. So you can go in between those two values, basically. Well, you can't really go in between, but you can pick one of those two values with the digital output. And again, we can loop through here. Let's say, let's do 4i in range of 10 again. And let's do D0 dot value equals true. Time dot sleep for half a second. D0 dot value equals false, so we'll turn it off. Time dot sleep for half a second. And we'll let that run. And check that out, we are blinking an LED. And you can see that the multimeter is also noticing the voltage change every half second there. So that's pretty cool. So that's basically a digital output. So I'm able to control this LED by connecting it to one of the digital outputs and then setting the logic level to a high or low voltage. Okay, so let's check out digital inputs next. So we can basically do the exact same thing of a digital pin as far as having an output, but we can do the reverse. We can say, I want to read whether I see a high logic level, a 3.3 volt logic level, or whether I see a ground, a low logic level. And this could be handy, for example, if you're using something like a switch. So this is a little three-way switch, a toggle switch, where there are 3 pins on the bottom of this switch right here. And the way this works is when the switch is in this position, it's basically connecting the leftmost pin to the center pin. And then when I flip the switch into that position, it's now connecting the right pin to the center pin. So think of the center pin as kind of the output of this switch, and then I can toggle it between being physically connected to either one of these sides right here. So I could have, maybe one signal that's on this side and now it's connected to the center, and then I have another signal on the other side and now that's connected to the center there. So the easiest way to start would just be to say, well, let's connect this center pin to one of the pins on my board, and then let's connect on the left maybe ground, and on the right 3.3 volts, the high logic level. So I'll give both of my digital logic levels, both the high and the low logic level, as possible inputs. And then when I toggle my switch, when I flip it in between, I should be able to read that value. I should be able to read a high or low logic value from there. So let's try that. Let's just reconfigure things a little bit on this board. So what I'm going to do is, actually I'm going to change the color. So let's take that red one away. And let's connect the green one to D0. And I'm going to connect this to the center pin of my switch right here. and we'll come back. I'm going to connect the other ones in a moment here. Before I get too far into this, let's first switch that D0 back to an input, because right now it's an output and it's set to a low logic level. But I want to be careful because, you know, if I connect up my ground and my 3.3 volts, the way this switch is set up, you know, I might accidentally connect like my 3.3 volt output of my board directly down to ground or something. I might short things out. So just to be safe, let's switch it to an input, because in an input state, basically this pin, this center pin, this D0 pin, won't be setting itself to any level. It's waiting to read a level. So it's not going to set itself high. It's not going to set itself low. So there's no danger that I might like short something out by, you know, having it set to a ground level and then connecting it to a 3.3 volt source, for example. Now to switch it to an input, it's pretty easy. There's a switch _to _input. And all of this is mentioned in the documentation here for the digital in-out object. So it basically has a function, like we saw, there's switch to output and switch to input now that we're using here. So I'm going to call switch to input. I'm not going to provide any parameters, but I'll come back and we'll see some parameters that we can specify here. Okay, so now I've got this thing as an input. And the way to read this, you use the exact same property, the value property. So d0.value, and this returns a true or false value. Now, it's going to be a little funny right now because this switch isn't connected to anything. I only have the center pin connected. That's connected to D0. I don't have a ground or a power pin connected yet. So I might just get random values. Like if I touch the sides of this thing, you know, maybe I get a true value. Look at that, it just changed to true, even though I was just literally just touching my hand to that. And again, that's because there's nothing connected to that. There's nothing that's pulling this down to ground or pulling it up to a high logic level. So let's change that. So let's connect the other two pins on this switch to the ground and to the 3.3 volt output of my Gemma M0 board. So for ground, let's see, let's connect this side of the switch to ground. So let's do that. And be careful not to let the alligator clips touch each other, because you know, you might get false readings or unexpected behavior that way. Okay, so I've got ground connected on that side, and then power, let's connect that to the other side of the switch. And power in this case, I'm going to connect it to the 3.3 volt output of my Gemma M0 board. So most development boards have a voltage output, and so that's what you probably want to use here. But again, be careful, make sure that it's the same logic level that your board expects. So if it's a 3.3 volt logic level for your board, like the Gemma M0, you don't want to connect a 5 volt source to that, because then you're going to send 5 volts into your digital input and you could damage it. It could be a bad thing. Okay, so I'm going to connect this 3.3 volts to the other side of this input. So let's see if I can do that without having to touch that pin to the other one. Oops, I think I'm actually touching it on accident. Let me connect that. There we go. Okay, I don't think anything's shorted out. Okay, so I've got this connected up, and you can see the way that the pin, or the way that the switch is in this position, it's connecting the red alligator clip to the green one. And then remember, that green one is connected to my D0 input on my Gemma M0. So I should see a true value now, because basically 3.3 volts should be connected to this D0 input, and we can actually see on my multimeter the voltage. It's still reading the voltage at that D0 input. So that's good. So it shows that this switch is probably working. But let's see what the value that we get back for this is. True. So that's good. And I can run this a few times, and it's true. It seems pretty consistent. It's not some random value. Now let's flip the switch. So I just changed the switch. And notice my multimeter just changed. It's down to 0 volts, so that's a good sign. It shows that the switch is physically working. And I'm going to read the value, and hey, now I get a false value there. So that's pretty cool. So I can flip the switch back, and multimeter shows 3.3 volts, and I get a true value when I read that. And I switch it back, and now we're connected to ground, and I get a false value again. So that's a digital input. It's basically just a true or false value. So imagine, you know, this switch, it's true if it's in the other position, and it's false when it's in this position right now. So it's an easy way to kind of know, is this switch turned on or off, like this. So let's do another little thing though. So there's some cool things. You know, notice the way I'm reading this switch. This switch has 3 pins. So, you know, it has one input, another input on the other side, and then kind of the output of the switch. And then it's going to connect one of those inputs to the output. But not every switch is like that. So here's another type of switch. This one's a momentary push button, where basically when I push this red button right here, then it's going to connect these two pins that are right here. So these two little pins on the outside. So I press the button and it's physically connecting those. And when I release the button, it's not connecting them. They're not connected at all. So this one's a little different in that, it doesn't have those three pins. And so you might be wondering, okay, well, how can I actually control this? How do I read this kind of a pin? And I'll show you. We can actually set this up so that the way it works is we'll connect our digital input to one of these pins on this switch, and then we'll connect either a ground or a 3.3 volt logic level to the other pin, so that when I press the button, it's going to connect them. Oops, sorry, so you can see this. So when I press the button, it's going to make a physical connection between those two pins. So my input will be connected to one, and let's say, how about 3.3 volts will connect to the other pin, so that, when I press the button, it's going to have 3.3 volts sent into my input, and so I should be able to read a true value. But when the button is not pressed, it's kind of a good question of what's going to happen. So that input's not physically connected to anything, and so it's going to be in the floating state that I mentioned before, where nothing is really is pulling it to a high or low logic level. It's just, kind of electromagnetic noise and interference might pull it up to a high logic level. It might pull it down to a low logic level. But that's a case where you can actually add something. Oops, my multimeter is angry. It wants me to do something. There we go. We'll just keep it happy. Anyways, so we can fix that though, that floating issue, because we can basically say for a digital input, I can add a resistor to it, a very low kind of current resistor. So it's not strong. It's not going to override a stronger signal. For example, if I connect like 3.3 volts to this, it's going to be a small enough resistor that it's not going to override whatever real thing might be connected to this. But if I connect a little resistor, then I can have it so that when nothing is pressed, that input is going to go to some logic level. Whether I have that resistor connected to a high logic level, then it's just going to naturally get pulled up to the high logic level when it's not connected. Or I could have it connected down to a ground level through that resistor, so that it's just going to be pulled down naturally to a ground or a low logic level in this case. So let's try this. Let's wire this up. So I'm going to disconnect my switch, and let's connect. So this green wire, again, this is connected to the D0 input still. So I'm going to connect that to one side of the switch right here. And I'm just going to cover this up a little bit so I don't short out the, there we go. So keep it from connecting the other side. And then I'm going to connect the 3.3 volts, the power, to the other side of this momentary push button switch. Okay, so it's now connected like that. So when I press the switch, it's going to basically connect these two. And so notice what happens. Just look at the multimeter. Don't even worry about the code yet. So I'm pressing the switch, and I see a solid 3.3 volts on that output, because, remember, the multimeter is connected to this green wire, so it's showing the voltage that's being fed into that digital input. So I press the button, it's connecting the red wire to the green wire, and the red wire is connected to 3.3 volts, so we're seeing that 3.3 volts on the multimeter. Now I'm going to release the button, and then watch kind of what happens. Like, it's all over the place. 3.9 volts. Maybe if I move my hand closer to here, is that going to change it? Maybe not. Oh yeah, if I touch this, like, look at that, it's going all wild. I went down to 0 volts there. So you're seeing that floating behavior that I mentioned, where this input is not connected to anything, and so it's just reading whatever electromagnetic interference happens to be around this device. But like I said, we can add a pull up or a pull down resistor to have it go to a logic level in this default state. And the cool thing is, a lot of boards have these resistors built into them, and the SAMD21 that's in the Gemma M0 and Circuit Playground Express board, it lets you actually control for all of your digital inputs whether you have a pull up or a pull down resistor connected to it. So pull up resistor will have it naturally pulled up to a high logic level when nothing else is connected and pulling it down. And a pull down resistor will have it connected to a low ground logic level when nothing else is controlling the pin. So because I have the high voltage level here, or the high logic level, connected to one side of my my switch, I think I want to have a pull down resistor so that when it's in this state, when nothing is pressing it, I'll read a low logic level. and then when I press the switch, it's going to connect it to 3.3 volts, and I'll read a high logic level. So, because I have a high logic level as my input to one side of the switch, I'm going to put a pull down resistor. I could swap this though. I could have ground connected to the other side, and then in that case I'm going to want a pull up resistor so that it naturally stays at a high logic level, and then when I press the button it connects it to ground and I'll read a low logic level. So it's kind of up to you how you're going to create a project. If you're using a button that's built into a board, sometimes it's designed in a certain way so that it expects to have a pull up or a pull down. Or for example, maybe the board actually builds in a pull up or a pull down resistor, and so you don't have any control over it. So something you might need to look at for your board if you're using something that has a built-in switch. Or if you're wiring up your own switch, then you can kind of make the call on what you want to use. Okay, so let's call that switch to input function again. But this time I'm gonna give it an extra parameter. So in the documentation it mentions there's this pull parameter, and this lets you control whether there's a pull-up resistor or a pull-down resistor. So you do that by saying the pull equals, and then it's in the digital I/O module. There's a pull class, and then inside of there are a couple constants that you can set. And so we can set either a pull up or a pull down. And so I want to set a pull down so that when nothing else is connected and touching this, when it's in this state, when the button is not pressed, and you can see it's floating like that, when I set this pull down resistor, it's actually going to pull the input down to a low logic level with a very small current resistor. So let's do that. And let's see what happens. Hey, check this out. So notice my multimeter just immediately shot down to like 0 volts basically. So, I'll put the range back down to the voltage. There we go. So you can see, 0 volts. So, the switch is not pressed, but it's naturally pulled down. I can move my hand around here and it's not floating, it's not changing. So that's good. That's what I expect. Now when I press this switch, we should still see, on the multimeter, notice it goes up to a 3.3 volt level. And then I release the switch and it goes back down to 0. So that's working the way I expect, like that. So let's read my input now. So let's go to the D0.value. So I read this and I'm getting false, which is good. I'm getting low. I'm getting the low logic level. Nothing is connected. That pull down resistor is giving me that false value. And then I'm going to press the switch, and while I'm pressing it, notice I get a true value there. So D0.value equals true. And you can see the 3.3 volts on the multimeter right there. So I release the switch, goes back down to 0, I get false, I press the switch, and I get a true value like that. So that's pretty much the basics of a digital input. I'm showing how to connect to a little momentary switch right here, and then by using the built-in pull up or pull down resistor, I can make it so that I can read this switch on this input by just feeding in either a high or low logic level, so that when the button is pressed, that logic level is connected to my input, and then I'll be able to read that value. And so, you just want to be careful in that if I'm connecting my input through the switch to a high logic level, then I want to use a pull down resistor so that when it's not connected, I get a low logic level. If I wanted, I could go back and I could switch this to a pull up, but now you'll see this is not a very useful switch at this point. So I'm going to do that. And so notice it's in a resting state and the voltage is up at 3.3 volts. I call D0.value. I'm going to get true, which makes sense because it's pulled up to a high logic level. But now my problem is when I press the button, it's also connected to 3.3 volts. So I also get true. And so now I've built a switch that I can't read the value of. It's always true. So maybe you could prank your friends with that potentially. But again, something to think about when you're using a switch like this, if you're using a pull up or a pull down resistor for this. Okay, so let's move on a little bit to show maybe something a little more interesting. I'm not going to show a demo of this, but I'm just going to mention, you don't necessarily have to read everything from just a switch. So there are other things that give you a digital output. For example, this is a door detection sensor, a little magnetic sensor where basically there's a magnetic switch inside of here on one half, and then there's a magnet on this half. And so when the magnet gets near this switch, it actually changes the output of the pins here. It makes a physical connection. And then when this magnet gets pulled away, then it disconnects these two wires right here. So think of it like this momentary push button right here. but it's just a magnetically controlled version of it. So there are two wires here, and basically these will be connected to each other when the magnet is close to it, and when the magnet gets pulled away, then they disconnect from each other. So it's, you know, as if I was controlling this switch, but just through the magnet. And this is useful because you could mount this to a door so that, you know, when the door swings open, it goes away from your little input, your reading side of this, and then your door closes and it gets next to that and it sets it off. Or maybe you have a window, and so, you know, you open the window and this goes up, and then you close the window and it comes down and it touches this and it's able to detect that, and you've got these two wires here. So let's just wire this up. I'm just going to connect it the exact same way that I had my my push button connected right here. So I'm going to connect the digital input, the green wire, to one of the wires that's connected to this sensor. So like I said, there are two wires that are connected to this, and then the other wire I'm going to connect to that red and that 3.3 volt signal here. And then I want to go back and I want to fix my code real fast, because remember I switched it to have a pull up resistor when I really want to have a pull down resistor for this. So yeah, let's switch this back to a pull down. And okay, so now when I read this, let's do d0.value. I get false, so there's nothing connected to this. You know, there's no physical connection on this switch. It's magnetic, so, you know, I can just read this all day and I'm going to get false because the pull down resistor is pointed down. But let's move this magnet next to it and let's see what happens. So, you know, imagine your door closes and now the magnet's next to it, and hey, check that out, I get a true value. If I move this away from it, then I don't know what the range is, but let's see what this is. So I get a false value, so that's good. So it looks like, you know, just it has to be within, you know, less than an inch. You know, maybe I move it like that, and let's see, do I get a true value? Yep, I get true, and then I move it away, and I get a false value like that. So that's pretty cool, and it just kind of shows that, you know, again, a digital input is a useful thing in that it doesn't have to just be a switch or an on or off signal. Well, it has to be an on or off signal, but it's not necessarily a switch or a button that provides that. So look around, there are all kinds of other things that give you that on or off signal. So this is like a magnetic switch. Oh, it's actually funny, I just noticed too, the multimeter kind of shows me too that, you know, when it's connected, when it's next to it, you see the 3.3 volts, and then when it's pulled away, then it gets disconnected there. So that's kind of cool. A little magnetic switch like that is a handy thing. Another type of switch is a slide switch. This is a lot like the toggle switch that we were just looking at right here, where it has 3 pins. So the slide switch is just like the toggle, but it just has a switch that is a little bit smaller, and it just moves in between these two positions like that. So that's another handy switch. And so you'd wire that up like the toggle switch. And Circuit Playground, it has built into it both push buttons. So these are these push buttons right here. So these are momentary push buttons that are just like the red button we were looking at a moment ago. And then it also has a slide switch in the center right there. So that's just an example. You've got 2 of those switches built into this board. Okay, so that's maybe a cool thing you can do with the digital input. You know, you can use a magnetic sensor like this. Let's go back and let's just look at the outputs again. And I'll just mention a few digital outputs that aren't just LEDs. So you can do more than turn on an LED. You could actually control something. So there are things like these. So this is a solenoid. This is a little micro solenoid, where basically it's a device. When I apply voltage to it, there's a little plunger right here. And this plunger can get pulled in or can get pushed out. I think on this device, I want to say the plunger gets pulled in when it applies voltage to it, but it might be reversed. Like, there are all different types of solenoids. But this is kind of cool if you're trying to actuate something. So, you know, maybe I'm building like a, you know, an internet connected light switch that I want to, like, I 3D print some enclosure that I put over a light switch on the wall. And then, you know, you can imagine you can have this a solenoid mounted right next to it that just, you know, maybe it starts in the off position and then it pops out to push your switch and, you know, flip your switch into the on position potentially. So you can move things around like that. This is a small little micro solenoid, but you can also get something big like this. This is a locking solenoid. This one's kind of cool. And it's same principle, so it takes in an input voltage, and when it gets a certain voltage, then it's going to move this little striker. And so imagine like a latch for a door. So the door closes, and then this thing might come out and lock or unlock the door, for example. So kind of cool little thing you can use for that. The one thing to be aware of though, so when you're using solenoids and things like this, they have different power requirements. So an LED just requires a little bit of current to turn on and off. Some of these solenoids require potentially a lot of current because they're using magnets inside here, electromagnets. Sometimes they require a lot of voltage, so you might need to wire up like a transistor or a relay or something that can control, given a small amount of current from your digital output, because your digital outputs on your board can only source maybe around 10 milliamps of current. You'll have to look at your board and the description of all the pins, but there's a limited amount of current, whereas some of these solenoids might require hundreds of milliamps or maybe even an amp of current if it's some really big beefy device. So your board's never going to be able to provide that much power. You have to use a transistor or a relay as kind of an intermediate source where you've got a nice big power supply, and then you're using your digital input or your digital output to switch that power supply on and off to control your relay. So just be aware of, this relay, it only needs a digital on-off signal, but there's more to it than that. You need to have the right voltage and the right current going to this. And so check out, we have a bunch of guides on how to talk to relays. Motors are also like this, although motors need a special type of signal that we'll see in a future video to control them. But like a servo motor, for example, requires a special signal. But like maybe a DC motor, you might be able to, if you're using a certain motor controller, control it with a digital output. Okay, so as a last little thing, let's hook this switch back up, and I'll just create a real program. And I was just thinking, I'm just going to create the simplest little example of using a digital input and a digital output. So I'm going to make it so that when I press this push button, let's have it turn on the red LED on this board. And when I'm not pressing the push button, we'll turn it off. So that, I press the push button, I want to see it basically turn on the LED. And when I don't press the push button, I want to see it turn off the LED. Oops, actually I wired up the wrong way. I want to connect the red wire. I want to connect my 3.3 volts to this switch. So I'm connecting the push button just the way I had it before. So I've got the voltage, 3.3 volts on one side, and then my digital input on the other side. So that D0, well, we'll come back to this. So I'm going to write a complete program now that I'll put on the board as a main.py, and we'll let this run, and we'll have it do both digital inputs and outputs. So I'm going to exit out of the serial REPL, and I'm just going to use the nano editor. Let's just create a main.py in this folder right here. Oh, I've already got one here that actually says hello world. So hey, look at that. Let's delete that. Okay, so let's import those modules again, like I showed earlier. So the board and the digital I/O modules, and then we'll just print out here. We'll say press the push button to turn the LED on or off. So we'll do that, and then let's create an instance of my LED, just like I did before, so that I can turn that LED on or off. So let's say LED equals digital IO dot digital in out, and that's the board.l object. And then I need to switch to output for that. And then let's create my button. So that's the D0 input. So that equals digital IO dot digital in out, and that's the board.d0 input. And then I want to switch this to an input so that I can control what that pole value is, because remember, I have high voltage, high logic level going into one side of the input, so when the button's not pressed, I'm going to want to read a low logic level with a pull down resistor. So we'll say the pull equals digital IO dot pull dot down, like that. Okay, so now I have my LED and my D0 objects created, just like I did in the REPL before. Let's just make a loop now, and I'm just going to, in that loop, read my input. If it's true, then let's set the LED to true. If it's false, let's set the LED to false. So this is actually going to be the world's easiest little switch or loop right here. So we'll say while true, loop forever. And actually, let's just set this to LED.value equals D0.value. It's really as easy as that, because when I read D0.value, that's going to give me a true-false value of whether the switch is, when it's pressed, it's going to be true, and when it's released, it's going to be false. And then my LED is working the same way. When I set this to true, it's going to turn on, and when I set it to false, it's going to turn off. So it's that easy. So we'll save that. Now let's save that, and then let's just copy this to my board. So I'm going to use the CP-uppercase X. This is just handy on Mac OS X. This will copy a file without copying any of this weird extra metadata. I've mentioned this in the Mac OS X video with CircuitPython, so it's a way, if you run into out-of-space errors, you might need to use the cp-x command. But let's copy this main.py to the volume, this is the drive that my board shows up as. So I'll do that. So I just copied it there. And so it should be running. Now I'm going to connect to the serial REPL just so I can see and debug any of the output, if something goes wrong. I'm going to press Control D. D is in dog. That's just going to do a soft reset because I want to make sure I see that output, that print line. So yeah, here we go. So it says press the push button to turn the LED on or off. Okay, so let's do that. So I'm going to press the push button. Hey, check that out. The red LED just turned on. And I'm going to release the button and it just turned off. So that's pretty cool. So, I press it, turns on, off, off. And then maybe just let's modify our program real fast. So I'll go back to the nano editor and let's just have it print a message maybe. So, it could be as simple as this, LED.value equals D0.value, or I could make it a little more advanced. I could say if D0.value, so if the button is pressed, then let's have it print out button pressed, and then let's set my LED.value equals true. So turn my LED on basically, and then else, so basically if D0 is false, if my digital input is false, then turn off the LED, and we'll print out a message also. So we'll say, how about, well, let's not print anything out because, if the button is not pressed, if I print something out, it's just going to constantly be printing that out when I connect to the serial REPL, which I probably don't want that. It's only when I press the button that I really want to see something happen here. So in that case, let's say LED.value equals false. So we'll just turn off the LED. So, okay, so we'll save that. And then let's copy that to my board and then connect to my serial REPL again. And so now when I press this, hey, check that out. It spams, it says button pressed, because it's checking very, very quickly. In that loop, I'm not delaying, I'm not sleeping or anything. It's just over and over, as fast as the board can check, it's checking that input. But I release that and it stops and it turns off that little LED. So I press that, LED turns on, and then I release it and my multimeter gets angry and turns off at that point. I hate the timeout on this X-Tech is way too short, at least for me. Maybe they never expected when they designed this X-Tech that people would be doing presentations that are an hour long with this thing. So they need to make the educator X-Tech that has a hour-long timeout on it or something like that. Anyways, though, so again, though, I just wanted to show this is a complete example of a program that's using digital inputs and outputs. And I'll go back, we'll exit out of here. And just to show you that code again for this is what it looks like. So, very simple, just like I showed before. You create a digital in-out object, and then you use either the switch to input or switch to output functions to control whether this is an input or an output. And then just depending on what I have connected to that, I can do different behavior. So I have a switch connected to my digital input, and then there's an LED built into the board that's connected to that digital output, so I can turn that on or off. Okay, so that's it. So if folks have questions, maybe throw them into the chat, although I don't see much there, so this will probably be pretty quick. Let's see, I'll keep that code open here. Maybe I'll switch back to the main view though, so we'll go back here. And yeah, so I don't see any questions. So I'll wrap up this video then. So this was the CircuitPython digital I/O, so digital inputs and digital outputs. How to control either a digital output. So you saw I have an LED that I connected to the board or was even built into the board. And we looked at how with a digital output, you can set it to a high or a high voltage logic level, which is 3.3 volts for this board, or you set it to a low logic level, a ground logic level, a 0 volt level. So you've got an ability to have an output where you can set it to a high or low logic level. So you might have a button or an LED connected to it that you turn on and off. But you could have like a solenoid connected to it. Another board that I forgot to mention, something like this. This is the audio effects board, where basically all of these pins on the outside of this board are inputs. And if I connect these to a digital output on my board, if I set one of these pins to a high logic level, it'll play an MP3 file out of this sound input here, or actually it'll play a WAV file on this board. So these are some boards where you can trigger sound effects where, you could just have this hooked up to a switch, maybe you have a trigger on a gun that you're building, or you could have this connected to a board like a Gemma M0, if you want your CircuitPython code to create sound effects. Maybe your board's not powerful enough to play back sound, or you don't have an amplifier or everything built into it, but you could connect a board like this that expects just a digital signal, like an input, high or low logic level to play a sound effect. So that's another example of something you might use with the digital output. And then we also saw how to use a digital input. So that's how to read a high or low logic level, like you might get from, a toggle switch like this. So you flip the switch into different positions and you're able to read that as a high or low logic level. Or we saw other different types of switches like this magnetic switch right here, where it can detect if a door is open or closed, for example, just by having these two connections connected together or not. So we saw how to read that with a digital input object. And we saw the importance of, with the digital input, sometimes having to use a pull up or a pull down resistor to control what's the steady state or what's the normal state when nothing is connected to this switch or this input. Does it stay at a high or a low logic level? Because in some cases, if my switch just has two inputs to it, I can't really control what happens when nothing is connected unless I have a pull up or pull down resistor. So we saw kind of the importance of that. But anyways, that's it. That's the digital I/O with CircuitPython. Like I said, this will be the start of a new series going back to all the basics of MicroPython. So looking at digital I/O, analog I/O, but in the context of CircuitPython. So CircuitPython is Adafruit's educational version of MicroPython, where the APIs are a little bit different and focused more on kind of beginners and teaching and showing how to easily control hardware. And so that's kind of the big difference between this and MicroPython. And I've actually done a whole bunch of videos on MicroPython, so I'm basically going back and redoing some of the MicroPython videos. So I did a video on digital I/O with MicroPython, and I'll put a link in the description below. You can check that out to see where I did the exact same stuff. But now I'm doing that with CircuitPython. So look forward to the next few weeks. I'll be doing more videos on CircuitPython and all the basics of analog, digital, talking to devices over like I2C or the SPI protocol. All that kind of basic functionality. We'll start doing revisiting that with CircuitPython. So anyways, check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I like to stream these videos live. And that's where you'll find me. Usually every Friday I do a video, so definitely check out Friday next week. I think I'm going to do analog stuff. So we'll see analog outputs and analog inputs. Analog outputs we'll see are kind of interesting. You use something called pulse width modulation to control an output. So we saw with the digital output, you can have on or off, but nothing in between. But we'll see with PWM, you can go in between. So you can set something that's halfway in between on and off, or maybe a quarter of the way. So we'll see how that works in next week's video. Anyways, click the like, the comment, the subscribe button. Let us know that this is cool stuff, and we'll keep doing content like this. Until next time, this is Tony from Adafruit, so thanks for watching. I'll see you later. Bye.